This is a solution to one of the problems from section 6.1. This is a problem where we have a particle moving along the x-axis according to some velocity function. The first question says to graph the velocity function, which I just did on a computer and put the picture in here. It got cut off over there on the right. It should go all the way to 7, but it just keeps going up. So from this picture, we can see that the velocity is positive above the x-axis between 0 and 4. Velocity is below the x-axis from 4 to 5, and velocity is positive again for t more than 5. So I can see the positive, negative, and positive velocities. Now remember, positive velocity, so that means that for these times between 0 and 4, positive velocity means that my particle is moving in the positive direction along the x-axis. So let me draw my axis down here. So imagine this is my axis. I don't really know where it's starting, so I won't try to label anything. But let's say that I'm here when time is 0. Then the graph tells me that for t going from 0 to 4, my particle is going to move in this direction. And then when t is equal to 4, it backs up and comes back this way to the right. So I have a negative velocity for t between 4 and 5, and that means I'm moving back to the left. And then it gets to here when t equals 5. And then at that point, it turns around and goes back the other way for a while until we get to t equals 7, and then it stops. So the particle is just moving on the x-axis, so I'm not suggesting that it's up here, but so it's coming this way, then back this way, and then this way again. And I don't know how far apart any of these things are. That's what the integral is going to tell us, is how far apart. So on the axis, I've just marked the times where the transitions happen. So time goes from 0 to time equal 4 to the right, then back to here when time is 5, and then back here when time is 7. And now I can figure out how far apart all of these transition points are by using integration. The displacement is simply how far are you at the end? How far are you here relative to where you started? And so you can move all around, but the displacement is just the difference between where you are at the end and where you were at the beginning. And that's just what the integral measures. So the normal integral over the entire thing here, and I won't try to do it. I guess I'll at least write down, here's the antiderivative of this creature, because we would have to use it several times if we're doing this by hand. So that's an antiderivative of the velocity function. This is the velocity function. It only takes a second to check that, like, the derivative of that is t cubed, derivative of that is 9t squared, derivative of that is 20t. So it's very easy to check that that derivative is that, which it's supposed to be. And then that gets evaluated between 0 and 7. And if I do that, I did that on my computer here, I get the displacement is 245 over 4, so 61.25. Now that's just how far you end up from where you started. What we want to know for part C is the distance traveled over the entire thing. So to do that, I can't just slap absolute value bars on the velocity function, and that is correct, but then to actually evaluate that and find the number, the absolute value bars have to come right back off again. So what I would suggest is trying just to add detail to kind of the story we're telling with these arrows. First of all, I'm going to say how far this arrow is taking me, because this arrow is only going in the positive direction, so I can tell you how far I go from 0 to 4. That's just the same integral from 0 to 4. I'm not going to do it's the same antiderivative, so I won't do it again. When I do that, I get 32 meters. So my journey starts by going 32 meters to the right in 4 seconds. Then I turn around and start coming back. Well, how far do I come back? Well, that's just the integral from 4 to 5. And if I do that, interval from 4 to 5, I get minus 3/4 of a meter. So that's how far back this way I go. And then I'm going to turn around and go right back to the positive again. And that'll just be the integral from 5 to 7. Of my velocity function. And if I do that, 5 to 7, I got 30. So the story is that my particle goes 32 meters to the right, then goes 3/4 of a meter back to the left, and then goes 30 meters again to the right. If you add those numbers together with both with the positive and negative signs, you get 245 fourths. That really is where it ends up. If you want to know how far you traveled, then you wouldn't count this as negative against your travel. You still traveled 3/4 of a mile, you just went a different direction. So the total distance traveled is just the sum of the absolute value of these things. So summing the absolute values would give me 32 plus 3/4 plus 30, which is 62 3/4, 251 fourths. And it definitely has to be further. You go further than you end up if you're backtracking. But again, with the story, that makes sense that I'm going 32 meters, then I'm going 3/4 of a meter, then I'm going 30 meters. If you ignore the direction, then this is true about how far you went in each of the three pieces. If you pay attention to direction, then you're going to add together these things with their plus and minus signs. So you'll get a slightly different answer. If you're backtracking, you'll have to, the distance that you end up away, the displacement will be smaller than the total distance traveled. The really extreme example of that, of course, is if you go out on the road and run half a mile down the road and half a mile back, you will have traveled a total distance of a mile, but your displacement will be 0 because you end up back where you started from.